In the last video we made out a probability distribution table for the number of heads showing on 3 throws of a fair coin. So that number runs from 0 heads to 3 heads. We said that the number of heads follows a binomial distribution. Generally speaking, the distribution of the number of occurrences of one of the 2 events of a Bernoulli trial over several such identical trials is said to be a binomial distribution. So in the example we did, we were looking at the number of occurrences of heads for the Bernoulli trial. So the Bernoulli trial was the throw of the coin, and there are 2 events, heads or tails. We looked at the distribution of the number of occurrences of heads. So we had several such trials. We had 3 trials actually for the coin, and the number of heads follows a binomial distribution. Now we're going to go back to the example of the coin that's thrown 3 times, and we're going to work out these probabilities without referring to the sample space. So last time, if you saw the last video, we looked at the sample space for the outcomes of a fair coin that has thrown 3 times. We have 3 identical throws. So we have 3 identical Bernoulli trials. So let's take A, where we have 0 heads. 0 heads means that we have 3 tails. What's the probability of getting tails on the first throw? Well, we know that it's a half, because we're dealing with an unbiased coin. What's the probability of getting tails on the second throw? Well, that's also a half. So the coin is unbiased, and of course we're dealing with independent trials. So we know that when trials are independent, then to get the probability of getting the 3 of them together, we multiply the probabilities. And we get 1/8. Of course, 1/8 is a much smaller number than a half. When we multiply numbers that are between 0 and 1 together, we get numbers that are smaller than them. So the probability is always a number between 0 and 1. Now let's consider the situation where we have exactly 1 head. So we're getting the probability of having just exactly 1 head, not at least 1 head. So let's consider how that can happen. Well, the first coin could show heads, but then the second and third coins must show tails. The probability of getting heads on the first throw is a half. The probability of getting tails on the throw is a half. The probability of getting tails on the third throw is a half. So the probability of getting heads on the first throw and tails on the second and third throws is a half times a half times a half, because we're dealing with independent trials, and this is 1/8. But this is not the only configuration that involves exactly 1 head. Here's another configuration. So we could have this or this. What's the probability of this configuration? Well, to get tails on the first throw we have a half. To get heads on the second throw we have a half. Tails on the third throw is also a half. So we have a half times a half times a half, which is 1/8. Notice that we get the same answers, no matter how these are arranged. Of course, we have one more configuration. We saw these configurations in the sample space. Again, now we've a half times a half times a half equals 1/8 for the probability of getting this configuration. Now, these are mutually exclusive events, and we need to apply the OR rule. We have this configuration, or this configuration, or this configuration. So the probability of getting 1 head, which I'll write 1H for short, is got by summing the probabilities for these 3 mutually exclusive events. So we have 1/8 plus 1/8 plus 1/8, which is 3/8. Now it's quite easy to write down the 3 configurations here, but you can imagine things getting more complicated. Suppose we wanted the probability of 2 heads in, say, 5 throws of a coin. It would get quite complicated to write down all the different possibilities. It's easy here. We know that there's only 3 of them. But how could we arrive at these 3 configurations? How do we know that there's just 3 of them? They're equiprobable. They all have the same probability of 1/8. Well, we could think of the number of ways of selecting one object from 3 objects. We could name each kind. We can call this kind A, this kind B, and this kind C. So what we've done is similar to getting the number of ways of selecting one object from 3 objects. And we have a shorthand for that. It's written 3C1. This is the number of combinations of one object from 3 objects. And we know from previous videos that 3C1 is 3. Well, you can just do it in your calculator. It's just a number of ways of selecting one object from 3. So, in the case of the kinds A, B, and C, here's one of the selections, here's another one, and here's yet another one. So we have 3 combinations. Or if you like, 3 ways to label one of the kinds with H. So we can see that the probability of getting exactly one head in 3 throws of a fair kind is 3C1 multiplied by 1/2 to the power of 3. So we are going to develop a formula for the binomial distribution. Now let's look at the probability of getting exactly 2 heads. Well, if the first throw is heads, the second throw is heads, and the third throw is tails, then the probability is 1/2 times 1/2 times 1/2, which is 1/2 to the power of 3. But of course, this is not the only configuration. The first throw could be heads, the second throw could be tails, and the third throw could be heads. We now have 2 tails, and the probability is here is 1/2 times 1/2 times 1/2 again, which is 1/2 to the power of 3, or 1/8. And we have one other configuration actually. The first throw could be tails, and the second and third throws could be heads. So the probability for each of these events is 1/2. So the probability of getting 2 heads, I can just write it 2H for short, is got by summing the probabilities of each of these configurations, because we have mutually exclusive events here. So our answer is going to be 1/2 cubed plus 1/2 cubed plus 1/2 cubed. Well, that's 3 times 1/2 cubed, which is actually 3/8. Now, let's see how we can count the number of configurations. Well, it's easy just to list them here, but for more difficult situations, we need to know how to go about it, counting them. So basically, we have the problem of selecting 2 objects from 3 objects. So we're labeling 2 of these 3 objects with a H. Labeling 2 of the 3 of them with a H is equivalent to selecting 2 of them. It's equivalent to finding the number of ways of selecting 2 objects from 3 objects, which is 3C2. And each of these events are equiprobable. The probability is 1/2 to the power of 3. So if we were selecting 2 objects from the objects A, B, and C, one combination is AB, another combination is AC, the third combination is BC. So AB is this first one here, if you like. AC, where A is marked with a H, C is marked with a H, is this combination, and BC is the third one. We can see that 3C2 is equal to 1. Sorry, 3C2 is equal to 3. To calculate 3C2, we could do it the direct way. We start with 3 and we multiply back so that we have 2 numbers on top, because we have a 2 down here, and we must have 2 factorial in the denominator. And if we simplify this, we get 3. As I've explained in an earlier video, 3C2 is the same as 3C1. Because when we select two objects from three objects, we always have one object left over. 2 plus 1 is 3. So by default, the number of ways of selecting two objects from three objects is the same as the number of ways of selecting one object from three objects. Lastly, we want the probability of getting three heads. Well, there's only one way that this can happen. And the probability is a half for each of these. So they're independent events. We multiply the probabilities together and we get a probability of 1/8. Now you could think of this as the number of ways of selecting three objects from three objects. So that's 3C3, but that's just equal to 1. So you could think of this as multiplying 3C3 by a half to the power of 3. So that's equal to 1/8. So this is the probability of getting three heads. Now I want to go back to the probability of getting naught heads. Getting naught heads is equivalent to getting three tails. And we saw that that's a half to the power of 3, which is 1/8. We saw that earlier. This number here is the probability of getting heads. I'm going to call this little p. This number next to it is 1 minus p, which is the probability of getting tails in this case. So this is the notation used in the formula for the binomial distribution. Let's look at the probability of getting one head. We saw that that's 3c1 times a half to the power of 3. Now we can write a half to the power of 3 as a half to the power of 1 times a half to the power of 2. So the probability of getting heads is a half. So this is the probability of getting heads. This number over here is the probability of getting tails, which is just 1 minus a half. 1 minus a half is a half. So we have one head and two tails. So as you saw before, we multiply these together, gives us a half to the power of 3, or 1/8. But then we multiply by the number of ways that exactly one head can occur, which is the same thing as the number of ways of selecting one object from three objects. So if you like, we're selecting one head from three kinds. Now we want the probability of two heads. We saw that that's 3c2. 3c2 times a half to the power of 2, because we have two heads, and we have one tail. We have a half to the power of 1. So 3c2 is the number of ways of selecting two kinds from three kinds. It's the number of ways that two of the kinds can show heads. Exactly two can show heads. The probability of getting two heads is a half squared. The probability of getting one tail is just a half to the power of 1. Finally, we have the probability of getting three heads. We can actually write it like this. We know the answer is 1/8, or a half to the power of 3. It is the number of ways of selecting three objects from three, which we saw is 1, times the number of ways of getting three heads in a row, it's half to the power of 3, times a half to the power of 0. So this number here is the probability of getting tails. But if we raise any number to the power of 0, we just get 1. So we're just multiplying this by 1. So we don't change the value of 1/8. We should notice some patterns here. The number of heads appears here, and it also appears here in our formula. The number of trials, which are throws of a fair kind in this case, appears up here. In general, that is denoted by the letter little n. Little n is the number of identical Bernoulli trials. The letter little r is used to denote the number of heads in this case. Well, in general, R is the number of events, or I should say the number of occurrences of one of the two events of the Bernoulli trial. Notice that if we add this number here onto this number, if we add the powers, we get n. See here as well, 2 plus 1 is 3. If we add these numbers, we get n. Suppose there are n identical Bernoulli trials, and we are interested in the event that has probability p. So remember, for Bernoulli trial, there are two events. One event has probability p. The other event must have probability 1 minus p, because the two events of a Bernoulli trial have probabilities that sum to 1. P plus 1 minus p is 1. So in the coin toss example, p was the probability of getting heads, which we know is a half. 1 minus p was also a half for the coin toss example, but of course p could be any number between 0 and 1. Let x be the number of occurrences of this event. So in the coin toss example, x was the number of heads in n throws of a coin, where n was 3. So x is a random variable. It takes on values with certain probabilities. In the coin toss example, x took on the values 0, 1, 2 or 3, and we calculated the probabilities for those values, and the probabilities have to sum to 1. So x follows a binomial distribution with parameters n and p. This twiddle means that x follows a binomial distribution. So B for binomial distribution, and the two parameters are n, which is the number of Bernoulli trials, and p, which is the probability of the event that we're interested in. The probability that x equals r, where r is the number of occurrences that we are interested in, is given by NCR times p to the power of r times 1 minus p to the power of n minus r. Notice that if we add n minus r onto r, we get n. The r's cancel out if we add the powers, just like we saw in the example. If we add these powers, we get n. Note here that r is a number running from 0 up to n. So in the coin throw example, r ran from 0 to 3. Now, this is the way you might see this formula displayed. Sometimes I prefer to use small letter x for a specific value of the random variable capital X. I just like to use this notation because these letters are consistent. Big X is a random variable. It can take on values, and little x is a specific value. Little x could be 0, 1, 2, any number up to n. So we would have x here instead of r. So sometimes I work with that notation, but I don't want to confuse people either, so maybe